Okay, so let's start with another seminar. Thank you very much for coming. Another Friday. And today is the day of Diego Vega. He's a PhD student at the Physical Oceanography and Climate Group. And he's working with Angel and Ananda, and I guess that he will be explaining his last advances in the PhD. So thank you very much, Diego. The floor is yours.
Thank you. Hello, everyone. I'm going to introduce you the use of remote sensing data and modeling for studying and identifying extreme sea level events. This presentation is going to be divided in 3 chapters. The first one is going to be explaining the SWOT capabilities, the update results of the SWOT capabilities for measuring extreme coastal water levels. Secondly, I'm going to explain my stay at CLS, which is the main company that processes satellite data. And finally, I'm going to explain the future work that I'm going to do. Okay, so the first introduction is what are storm surges? Storm surges are rapid and abnormal sea level rise due to the effect of storms blowing against the coast. So the factors that influence most of the storm surges are the wind setup, which are the strong winds blowing against the coast, which are accumulating the water on the coast, added to the influence of the low atmospheric pressure, which raise the seawater level 1 centimeter per hectopascal drop. Then added to the wave setup, which is the constant breaking waves on the shore. And finally, the sea level rise is influenced by the topography of the coast, where in narrow and shallow inlets, the water, when it's forced within it, is not able to escape from the coast and is forced to rise. So in this context of extreme events, this is an example of the consequences of storm surges. This is one example of Hurricane Ian in the United States, and the storm surge reached 4 meters, and we can see that it's catastrophic. Okay, so for monitoring this type of events, SWOT, it's a new satellite that they launched in 2023, and it's able to obtain 2-dimensional images of the sea surface state. With previous altimeters, satellite altimeters, we could only measure 1-dimensional along track measurements, and with a sparse resolution, about 7 kilometers of resolution each dot that we see over there. And with SWOT sensor, with Karin sensor, which is integrated in SWOT satellite, we can observe 2-dimensional images over 2 wide SWOTs, which allows us to see finer details, as we can see in both examples, with 2-kilometer resolution. There are new products, well, new, no? The products that are derived, the original products are 250 meters, but after processing, we can obtain 2-kilometer resolution of this data. And we can observe the shape of hurricanes and even storm surges on the coast. And the exceptional and the interesting data is that we can obtain even data on ports that with previous altimeters that was not possible. So for validating SWOT data, we use tide gauges that are ground-based measurements on the coast. That is a traditionally way for measuring and monitoring storm surges. And we are going to use that as ground truth. Later, we are going to use the SWOT data, in which we have added the atmospheric forcing for having the atmospheric influence on the data. And we are going to use as auxiliary dataset SKIS model, which is a state-of-the-art hydrodynamic model, which is forced with wind and pressure fields from ERA 5 and allows us to simulate storm surges. So from those both datasets, we are going to create time series at each tide gauge location. And then we are going to compare them. So when we select the most extreme events detected by SWOT, we are going to check the atmospheric conditions with ERA 5 reanalysis model for validating the proper conditions for developing storm surge. we are going to take the wind and pressure fields from ERA 5. So the study region, from all the tide gauges selected, or from all the stations studied, we are going to select, first of all, one in macrotidal region, which is located in a Topography location, which is in the North Sea, and another one which is in macrotidal region, that is Kiel Station, that is in the Baltic Sea. So, as we said before, we created first for the Altevessel station, we created time series, where in black is the record of the tide gauge, in blue is the time series of the model, and each red dot are the SWOT measurements at the location of the tide gauge. So we select the most extreme events. From those, there are not, one of them is not the most extreme event, but we selected those because the SWOT track is perpendicular to the coast, which allows us to see the extent of the storm surge. So we selected those extreme events. And first of all, we're going to check the atmospheric conditions, where in black here we see the location of the tide gauge, and the atmospheric conditions show us a low atmospheric pressure, which is located there, with minimum pressures of 964 hectopascals, and strong winds blowing against the coast of Denmark and Germany. This tells us that is the proper conditions for developing storm surge. Then we check the model, the skills model, and we can see reflected the influence of the atmospheric forcing on the sea level. And finally, we can observe the spatial extension that SWOT detected over the two white spots, that we can agree before checking the time series that in amplitude there is good agreement between SWOT and the tide gauge, and the error was lower than with the model, than compared to the model. So we can agree that it has better results than the model in that specific measurement. And we can see the extension of the storm surge. In the second extreme event, we can observe again strong winds blowing against the coast of Denmark and Germany. However, here the model doesn't reflect what SWOT is measuring, because sometimes the models, because of the forcing that they have, that the resolution spatially and temporally is not so accurate. Sometimes they don't measure correctly the storm surges. However, SWOT is able to see to detect the extension again of the storm surge. So this is for microtidal regime. Then from microtidal regime, we can observe the difference in variance on the time series due to the microtidal regime of the area. And again, we can observe in black the tide gauge, in blue the model, and each red dot SWOT measurements. And again, the error is lower than with the model. And we are going to check those both measurements of SWOT. And again, the winds are lower than in Altevessel, but it's not necessary to have stronger winds than in the previous one, because of the orography of the Baltic Sea on the north, on the southwest. It has shallow waters, and all the water that is being pushed is focused on one narrow inlet bay. So when checking the model, we can observe how the storm surge is formed and how SWOT is able to measure the storm surge with good precision, and is able to measure the northern part of the islands of Denmark. That this is sometimes difficult to measure because the model resolution and the model resolution is not always the best. So it allows us to check better than the model how in inlets and in difficult orographic regions, SWOT is able to measure correctly. This is another example. Again, strong winds blowing against the coast, stronger winds than before. And the model represents quite good the storm surge. And then SWOT has more amplitude in the results. It's higher, the sea surface height. And we can observe that there is a huge gradient between the north part of the islands of Denmark and the northern part. We can observe how all the water being pushed against the southwest of the Baltic is being closed through those islands, and the wind is blowing like northerly. So the water in that place is northern to the islands, is being forced out of the sea, and in the south is being closed in that area, so it's forcing the water to raise. And then another example is checking SWOT during hurricane conditions. This is a case of Hurricane Milton, where SWOT crossed the hurricane track 8 times. This is 7 times, and 2 of those tracks intersected with 2 tide gauges, which allows us to validate the SWOT measurements. Okay. So here again, in the lower part of the figure, we can observe the time series, where both have good agreement with the SWOT measurement and the tide gauge, and their error is quite small. And in both time series, during the hurricane conditions, SWOT measured the most extreme values from all the record with good agreement. And then checking the maps, we can observe the center of the hurricane, and the strong winds are described by the arrows. And here in Theta del Carmen, that is this tide gauge, we can observe how the storm surge its extension, we can observe. And in the right panel, we can observe how SWOT intersected directly the eye of the hurricane, which allows us to see the influence of the atmospheric forcing on the sea surface height quite clearly. Okay, and with it allows us to validate not in the eye of the hurricane, but in the outer part of the hurricane with good agreement. So the highlights of SWOT for this type of events is that it's being able to measure the amplitude in different tidal regions, is able to capture the spatial patterns of the hurricanes or storm surges, and it can be useful for validating hydrodynamic models. And for future works, it can be used for creating virtual tide gauge stations in areas where there is lack of tide measurements. Okay, so from this study, I started a stay at CLS, which is a company that is specialized in treating satellite data and is focused on processing level 2, level 3, and creating level 4 maps. And it's quite big, the company. So at this company, I worked a little bit of the level of the editing of the data of the level 3. Then they created a DAC. DAC is the dynamic atmospheric correction, one correction that is applied to the SWOT measurements, and they developed a new one that has higher resolution, spatial and temporal. And one of my works was to integrate that data into SWOT measurements. And the final work that I did is to validate the L4 products that are gridded maps that they create, and they need validation for that. So the different levels of editing the data, we can see here. This is the unedited data, like the raw data. Secondly is the edited, where they have dropped all the data based on different flags, depending on if it's outlier, if it's coastal related, the bad measurements, landmass, and different types of problems that can have the measurements. And I worked on checking which one is better for validating the extreme events, because it's expected that during extreme events, there are more outliers and they are dropped directly from the product, and they don't have a pre-assessment specifically done for extreme events. So I checked a little bit this in coastal areas too, because we can see that there are gaps on the data that actually, if you check on the raw data, can be useful during extreme events. And some of the results, this is the same type of plot that I showed of the time series, tide gauge and SWOT measurements with its different levels of dating. And we can observe that there is more or less same results for the three of them during all the measurements. However, there are some tide gauges that, if we check the extreme events, the SWOT measurements has less error when it's unedited in the product. So this is the thing that we have to still be working on, because it's not in all the tide gauges, so it depends on the region. And the next work was to, as I said before, the DAC, the atmosphere, the altimetric satellites has different corrections, and as I said before, at CLS they developed a new DAC correction, and I tried, well, I interpolated that DAC into the SWOT measurements and checking the difference with the DAC that they usually use. And as it has much better resolution spatially and temporally, there are quite huge differences during hurricane conditions, 7 centimeters, 10 centimeters, not that huge, but it's something to consider, that to use the new DAC correction. Well, and first we have to validate which one is better, but we still haven't have the coincidence of hurricane, SWOT, and tide gauge for validating it. So it's a thing that we have to still work on. This is another example of differences. Now the new DAC, it's subestimating the DAC, the atmospheric forcing. However, in the other one, as we saw, is overestimating. So this is the thing that we have to continue studying. And finally, to explain this, as we explained before, the traditional altimeters, they use nadir sensor. So when you mix all the nadir sensors from all the satellites, we can interpolate them in time and in space and create maps. Instead of along track measurements, we can obtain directly maps. And at CLS, they are the ones who create this type of products. And another work is what it was to validate these measurements in all the tide gauges from Europe. And this is one example of we obtained. And I compared 4 different products, sea level anomaly multi-year, near real time, and MIOST. That MIOST is a method of interpolation that includes SWOT measurement. So it's really useful because, as we saw, SWOT can measure 2-dimensional images, so it's supposed to have better results. And yeah, surprisingly, the multi-year for most of the tide gauges has better results, but because it's a reprocessed product. And then the second one was MIOST and MIOST V2 version 2, which is with some corrections applied. Yeah, that was what I did. And then future work. The group of Marta, they created, this is apart from what I have done before. Okay, so they created a scissors phase temperature field without the effect of the global warming on it. So the future work is going to be focused on and modeling the atmosphere during extreme events, during hurricanes, and use as forcing Era 5 fields, and to use Era 5 fields and the field of sea surface temperature, because for hurricanes, what gives the power is the sea surface temperature. So it's one of the most important parameters for modeling it. And I'm going to do the simulations with the counterfactual field and without the counterfactual, for then comparing the difference of the anthropogenic forcing. Then I'm going to use that output as an input for the hydrodynamic model for checking how the anthropogenic forcing has been influencing the storm surges. The result probably is going to be to check the impact of the anthropogenic warming on extreme atmospheric and sea level events. Yeah, that's well. This is a product that it's available for everyone, and you can use Task Ananda because it's really useful for all types of studies that want to check the influence of the global warming. And yeah, contact them because I think it's really useful. And that would be it. Yeah.
That's Diego. Interesting. Any questions for Diego?
Thank you. I'm not sure I understand it well.
Okay.
But this is about the outliers. So if I understood it well, the normal thing is that the programs or products, I don't know how you call it, remove the outliers. And then for the extreme events, you show it was better to not remove them.
In some specific cases, I showed one because it was interesting to see that the non-edited measurement, it was better, but in other cases
That was my question. So the outliers are actually measurements that are much higher than others, right? But this could be because of an error in the measurement or because it is like this.
Exactly.
So how do you know? And do you think it's right to remove the outliers in general? Or how can you get an error in the measurement for that? Or
just validating it with in situ measurements, because yeah, the results can show one thing, but if you don't validate it, you don't know what is correct or not. So in some moments, it can, for the extreme events, it's difficult to have the validation data. So I just obtained the results. And now when there is going to be more hurricanes that intersect SWOT with the hurricane with tide gauges or another in situ measurement, it can be continued, this study. But if there is no...
in case that there is no an extreme event, in normal, it's known that it's better to remove the outliers.
Yeah, well, yeah, I would say. I haven't confirmed it, but they are doing it for, there is a huge team of people who validates that measurement. So I trust that is correct as they do it.
And do you know what's the source of these kind of outliers? Why it's
there are
measuring very high values in some cases?
There are these corrections, instrumental, environmental, this type of errors that you can try to solve these errors, but the instrumental errors, I think the environmental, I mean, all these corrections are mostly models, and every model includes some error that you can guess.
Errors are bigger close to the coast.
Errors are bigger close to the coast, exactly. So
precision from land to
Uh-huh.
ocean. And we have to remember that the satellites are about 1,000 kilometers above the sea, and they measure with the precision of 1 centimeters. So it's 1,000 kilometers, 1 centimeters. And this is thanks also to the all the improvement that have been done in more than 30 years in the community. So the errors were about 1 meter
Mhm.
in the 70s, and now it's 1 or 2 centimeters. And so every correction plays a role.
Mhm.
And there are people who are just focused on improving what the system bias, the water atmospheric correction, because this is a pulse, an electromagnetic pulse, like light that propagates in the air, in the atmosphere. So if it was in the was not no atmosphere, it would be like 300,000 kilometers per second. But since we have troposphere, we have E1, we have different kinds of particles in so the velocity of propagation is different, and so you have to try to estimate in order to have the height. So you have the time that it takes the pulse to go from the satellite to the sea, and then you have the velocity. With time and velocity, you can estimate the height, but the velocity is not constant. And also there are orbit errors because satellite can change, and so there are many corrections. And at CLS, people are just working on different
Yeah, completely.
corrections.
Uh-huh.
So it's a really team effort.
Cool. Yeah.
In these hurricane conditions, you saw that the poor data quality was also due to the cloud cover, no?
Yeah. Cloud cover,
In
it's
hurricanes,
effective.
you have obviously a lot of clouds.
Yeah, but surprisingly, I saw in some pictures, like the one, wait, no,
Like there.
wait, here. Supposedly, I checked the images and the clouds are bigger than we can see, and SWOT is able to capture in some, I guess it's in the less dense parts of the clouds. Actually, I don't. This is another thing that I have to study, but there are plenty of things that I don't really know. But yeah, it's working.
So I'm interested in the assumption that you can use the tide gauge as a ground truth. Okay, I know nothing about tide gauges, but instruments in general can fail, right? They have a range of applicability. So in particular, I would guess that it's more likely that they will give you an erroneous measurement if you are in extreme events, and you're using them as ground truth in extreme events as well.
Exactly.
So how is it possible to test further the reliability of the tide gauge data for extreme events?
Well,
Because you're using those, right?
Yeah, completely.
But maybe the other things are better, and
I
they
don't.
perform better in those circumstances.
Yeah, but in the coastal areas, another type of measurements, in situ measurements, all of them are going to be influenced by extreme events. So yeah, it can be. We need to use that as a ground truth because we don't have another thing to validate with. If you have another, or do you think another in situ measurement that can be used, I will be interested because I want to validate all this. Because if not, it's not useful to me. So there is another thing.
I don't know.
Okay.
It's not my field, but you know, it's if you rely. I mean, it's always questionable to rely 100% on measurements of a single type. Right?
Yeah, completely.
To ground a bunch of other stuff that you're going to do afterwards.
Yeah, there is HR radar that can be used, but during extreme events, I think you can tell me that if it's has.
No, the best thing that we can do in this case is to compare tide gauges that are closer. So we try not to use just one tide gauge, but a set of them, and this. So we reduce somehow the uncertainty of the error of one tide gauge, and then there are also problems. If the stream event is very intense, maybe the tide gauge is swept away.
Mhm.
So sometimes we don't have measurements. It's difficult to validate the measurement, the models in the streams event.
So, no more question.
Okay, so we can stop here. Thank you very much.